Welcome back to our calculus course. In our previous lesson, we studied exponential functions. Today, we continue that discussion by introducing logarithmic functions. Suppose we know that 2 to the 5th power equals 32. This equation tells us that if we raise 2 to the 5th power, we obtain 32. But now let's ask a different question. Instead of asking what is the value of 2 to the 5th power, suppose we ask to what power must we raise 2 in order to obtain 32? The answer is, of course, 5. Instead of writing this answer in exponential form, mathematicians introduced a new notation. Logarithm base 2 of 32 equals 5. Notice that this equation contains exactly the same information as the exponential equation. The only difference is that we are now solving for the exponent. This is main purpose of logarithms. A logarithm tells us which exponent is needed to produce a given number. In other words, logarithm answers the question, what exponent? Once we understand this idea, logarithms become much less mysterious. Let's write a formal definition. A logarithmic function is written as y equals logarithm base a of x, where base a is positive and not equal to 1. This equation is completely equivalent to the exponential equation a to the power of y equals x. These two forms express exactly the same relationship. One is written in exponential form, the other is written in logarithmic form. Learning to move easily between these two forms is one of the most important skills in this chapter. Notice that a logarithm has 3 parts: the base, the argument, which must always be positive, and the value of the logarithm, which represent the exponent. Remember this important fact: a logarithm is not a multiplication, is not a fraction. It is simply another way of writing an exponential relationship. Now we arrive at one of the most beautiful ideas in mathematics. In our previous lesson, we learned about inverse functions. An inverse function reverses the action of another function. Exponential and logarithmic functions have exactly this relationship. If f of x equals a to the power of x, then its inverse function is f inverse of x equals logarithm base a of x. This means that whatever the exponential function does, the logarithmic function undoes. If we first apply the exponential function and then apply the logarithm with the same base, we return to our original value. Likewise, if we first apply the logarithm and then the exponential function, we again recover the original value. Graphically, this relationship is very easy to recognize. The graph of the logarithmic function is simply the reflection of the exponential graph across the line y equals x. Notice how the domain and range are exchanged. Let's compare exponential and logarithmic functions more carefully. For an exponential function, every real number can be used as input. Therefore, its domain is all real numbers. However, its output are always positive. This gives the range of the exponential function. Now consider the logarithmic function. Since logarithms ask the question, what exponent produces this number? The input must always be positive. There is no real exponent that allows a positive base to produce zero or negative number. Therefore, the domain of every logarithmic function consists only of positive real numbers. On the other hand, the output of logarithmic function may be positive, negative, or zero. As a result, its range is all real numbers. This comparison clearly illustrates how inverse functions exchange the rules of the domain and the range. Understanding this idea will help you avoid many common mistakes when solving logarithmic equation later. At this point, we understand what logarithms are and why they exist. The next step is to learn how to work with them efficiently. Just as the exponents have their own algebraic rules, logarithms also have a set of powerful properties that make calculation much easier. These properties are direct consequence of the law of exponent that we reviewed earlier. The first is the product rule. It tells us that logarithm of a product is equals to the sum of the logarithms. Instead of finding the logarithm of an entire product, we may find the logarithm of each factor separately and then add their results. The second is quotient rule. The logarithm of a quotient is equal to logarithm of numerator minus the logarithm of the denominator. Notice how multiplication becomes addition while division becomes subtraction. If the argument of a logarithm is raised to a power, that exponent may be moved in front of the logarithm as a coefficient. These identities allows us to simplify complicated expressions and are essential for solving logarithmic and exponential equations. As we work through example, we will see how powerful these rules really are. Although logarithm may have any positive base except one, two particular bases are used much more frequently than all the others. The first is base 10, called the common logarithm. Instead of writing the base every time, mathematicians usually write simply log of x, where the base 10 is understood. The second is natural logarithm, whose base is the special number e, which is approximately 2.71828. The natural logarithm is written as natural log of x. The number e is one of the most important constants in mathematics. It appears naturally in calculus, differential equation, probability, statistics, finance, engineering, physics, and machine learning. As you continue studying calculus, you will discover that functions involving e have remarkable mathematical properties that make many calculations much simpler. For this reason, the natural logarithm is often more important than logarithm with other bases. Logarithms also appear in many scientific measurements. For example, the Richter scale measures the magnitude of earthquakes using logarithms. An increase of 1 unit Richter scale represents an tenfold increase in the amplitude of seismic waves. Similarly, the decibel scale, which measures sound intensity, is logarithmic. This allows us to represent an enormous range of sound level using manageable numbers. These examples demonstrate that exponential and logarithmic functions are not merely mathematical concepts, they are powerful tools for understanding and modeling the world around us. Let's see how logarithms help us solve exponential equations. Our first example is 2 to the power of x equals 16. Since 16 is a power of 2, we can rewrite it as 16 equals 2 to the 4th power. Now, both sides have the same base. Therefore, the exponent must be equals. This gives us x equals 4. Now consider a slightly more difficult example. 3 to the power of 2x minus 1 equals 81. Again, we recognize that 81 equals 3 to the 4th power. Since the bases are equal, we set the exponent equals. This gives 2x minus 1 equals 4. Adding 1 to both sides, 2x equals 5. Finally, x equals 5/2. But not every exponential equation can be solved by rewriting both sides with the same base. For example, 2 to the power of x equals 7. Since 7 is not a power of 2, we apply the logarithm to both sides. Using the properties of logarithms, we obtain x equals the natural log of 7 divided by natural log of 2. This demonstrates why logarithms are so useful. They allow us to solve exponential equations that would otherwise be impossible to solve using elementary algebra. Now let's solve equations involving logarithms. Our first example is logarithm base 2 of x equals 5. Remember that a logarithm tells us the exponent. Therefore, we rewrite the equation in exponential form. This gives x equals 2 to the 5th power, which equals 32. Let's consider another example. Suppose we have natural log of x minus 1 equals 2. Again, we rewrite the equation in exponential form. Since the base of the natural logarithm is e, we obtain x minus 1 equals e squared. Adding 1 to both sides gives x equals e squared plus 1. Whenever you solve a logarithmic equation, always check the domain. Remember that the argument of every logarithm must be positive. If your solution makes the argument 0 or negative, then it's not a valid solution. Checking the domain is one of the most important steps in solving logarithmic equation and helps eliminate extraneous solutions. Now we have learned how to define logarithms, use their properties, and solve both exponential and logarithmic equations. Thank you very much for watching. If you find this video helpful, please give it a like, share it with your friends, and subscribe to the channel. Until next time, keep thinking mathematically.